All right, so today will be a relaxed class like the last time we did review. Uh, just a few things. First, I didn't write this down, but for those on iPads, this PDF was uploaded just before I came here, so you could find a link sort of in the appendix chapter if you wanted to kind of annotate this PDF instead of whatever else you're using. Otherwise, uh, yeah, I'll mention that uh, uh, in general, I usually have office hours as long as people have questions. So, you know, they'll probably be going longer today. That's often the case before the exam. Uh, and today I'm just going to put up questions to give you some time to work on it, maybe as a group, and then walk around answering questions. But in that time, I'm also happy to answer any other kind of questions you might have. You can kind of treat it as a hybrid office hours slash review. Um, the PSO this week is just review problems. We encourage you to take advantage of it. Some of them aren't very crowded, so you can even just go in and just ask whatever question you have. It probably wouldn't be that disruptive. Um, and then there's a little bit of confusion on some of the answers for problem 9.2. So we thought that maybe we could add a hint and give people a second chance to do it if they wanted, or they can just let the deadline pass. That's fine. But we thought maybe some people uh, uh, would want to adjust some things with a little bit of additional clarification. So that deadline was extended to tomorrow night at midnight. Okay, but the other two solutions should be out. Any questions? And you can always ask me as we get started. Okay, so I don't know. I put this kind of as an optional problem once before, but I don't know if you guys have actually tried it. If you have all tried it, then maybe we would skip it, but it's a fun one. Um, okay, so, all right. So this problem is called racetrack. Um, and I guess it's a simple game, but okay. So what's the high level? Can you guys read this? Is it too small a font? Okay, let's scroll through. Okay, so it's sort of a race car type of game with a grid of sorts. I guess we'll give you an M by N grid, but here's a 16 by 16 grid. And uh, so some of the tiles that are white are like places the race car can go. Um, Other tiles that are shaded dark is where race cars can't go. And you have some tiles that are marked as starting and some tiles that are marked as uh, ending. Okay. And so so you get to choose the starting location. You can choose any starting location you want, and of course the goal is to try to get to an ending location. And so at some level, it's some kind of like the car always has a certain velocity, at each step, and you can adjust the velocity by a small amount in each round. So initially, you might start at uh, here, and the car just has zero velocity in the x and y direction. Okay, and you might say, okay, I want to accelerate so that I'm going speed 1 in the x direction and still speed 0 in the y direction. Which case you can go then to here. Um, uh, and right now the car has velocity 1 to the left and 0 up or down. Okay, so each round you're allowed to change sort of the x velocity and the y velocity by 1. Okay, so in the next round, this car decides to go faster in the horizontal direction. So now its x velocity is 2 and it went down by 1. So it changed its y velocity by 1. And then you'll see in the next round it changed its y velocity back to 0, and its x velocity became even bigger to 3. So each round, so your car has a position on the map and also x and y velocities. Okay, and so each round you can change the x and y velocity by 1 each. Okay, and then you update your position based on adding that velocity, so to speak. Okay, so you can only accelerate so much for each turn. You can only go 1 unit faster. And if you start going too fast, then you might not be able to steer sharp enough to stay inside the white region. Okay, so you can't just go all out. Okay, so do those high level rules make sense? Okay, so the input then consists of one. Okay, the input consists of. Sorry, this thing's so annoying. Okay, the input consists of an n by n array of bits, where a 0 will represent that's a place the car can be. A 1 will represent where it can't be. And I guess you're allowed to start anywhere you want in the first column and anywhere you want in the last column, but it has to be one of the legal racetrack squares. And okay, so for this problem, make an algorithm or show it's hard. It's not hard. Okay, so that's the high level question. So give an n by n grid that represents a racetrack. You can start anywhere on the left, try to figure out how to get to the right in as few steps as possible. The question makes sense? So a problem out of Jeff's book. I think it's one of the suggested problems. Oh, you can't hear. Oh, this is a problem from Jeff's book, and I think it's one of the suggested problems because I always think this is a fun one. Otherwise, I'll let you guys just work on it. I encourage you to talk to each other, work in groups or something. It's more fun, and then I can just raise your hand if you have a question. Oh, it might be worth reminding you that many problems can be solved by either identifying the right subproblem or changing the input to something we already know. Yeah, so the input describes the track. I don't know if you can see, but so I give you an n by n array, and it just says yes or no. It's to race track or not. Yeah. Daniel, did you already solve it? No. Oh, okay. That's fine.
Generating what I want to do. Like
Okay.
if like each big point is like a vertex on your path,
Mhm.
and then you connect like if you have like this as a vertex and you connect edges between all the neighbors of that are still like one.
Yeah. So so that's a good first step, and that would sort of if the car was only going velocity one and one and stuff like that. But of course, the part that doesn't quite capture is the car can speed up or slow down, right? It can ramp up to velocity two and take two steps, and velocity three and take three steps.
Well, can we not only increase it by one? I thought it was.
You can increase the velocity by one each round. So in other words, he can be going 1 mile an hour the first round, and then 2 miles an hour the second round, and 3 miles an hour the third round. So he can speed up. So it's hard to see, but you can sort of see that the lines between the circles sometimes stretch out and shrink. They're not the same size. So each time it's accelerating by so your acceleration is bounded by one. but this is you're doing the this is the first step that you got, and then now you have to figure out kind of how to incorporate a little bit more information. Nehal, right? Okay. Did you figure it out?
Well, I have something, but I created a lot of different subproblems, so I don't know if that
Oh,
will
interesting.
remain polynomial.
So what I had in mind wasn't, at least directly, actually a dynamic programming solution.
Okay.
It was the other category. Although maybe there's an implicit connection.
Mm-hmm.
But yeah, what I had in mind was actually a little bit more in the change the input
Oh, okay.
variant.
Okay.
Possibly you're right anyway, or you do something slower. But you
Yeah,
can also
I
explore that.
feel like with this many different subproblems, it would either be not polynomial anymore or just really slow.
Yeah, or at least a bigger pain in the ass than I would. Oh, this is recorded. A bigger pain than I would want to put on the test.
Yeah.
Yeah,
Yeah.
maybe I'll take a temperature. Uh, okay, I thought maybe I could just take a quick poll. I think we're still working on it. Is that true? Okay, and it's a fun problem, so I'll let you keep going. But I thought I'd just kind of keep us steering on the right path. No pun intended. Um, is anyone leaning towards NP hard? Okay, so most people are trying to give an algorithm. And then if I told you it's one of the two categories, loosely speaking, of trying to identify the right subproblem and doing something like divide and conquer, dynamic programming, or trying to do some kind of change the input, some kind of reduction, do some other algorithm we've done like shortest path or max flow or something like that. Uh, I thought maybe I could still take a poll. And who's trying to pursue a identify the subproblem approach? Oh, okay. I'd say like 60%. Oh, I don't know who's not going to vote, and who's going for some kind of reduction. Okay, much less. Okay. Uh, okay. Then I will give as a hint then that actually, at least the solution I have in mind, maybe there's a way to do it both ways. But what I had in mind was something based on changing the input, change the graph, not the algorithm. Now, often there's some connections. Some of the graph algorithms can be understood as dynamic programming implicitly, but I would still categorize this. back here. But the PDF is also posted on the course notes, like in the appendix under practice problems. Uh, sorry. Oh, okay, yeah. So yeah, you can see it there. You guys solve it? Okay, fine. So it looks like people are still working on this, right? Or not? Did you guys solve it already? No, not yet. Okay, let's okay, fine. All right. I don't know if anyone solved it yet, but maybe we can at least try a first idea that'll get you halfway there and figure out what we're missing. And I give one more chance. Uh, so for those who are trying recently to try to change the input, and maybe you haven't quite figured it all out yet, but what are some ideas that they might have tried, or maybe things they would try to change the input to? Yeah.
Just for every cell, going into all other reasonable cells and then run BFS.
Okay, so at some level, okay, so what I saw from several people was trying to do something like shortest path, maybe BFS or Dijkstra. Okay. And that at least is a reasonable first guess, since we are trying to kind of get from point A to point B as fast as possible. At least that would seem most similar to a shortest path problem. And then, the next step is making a graph. And what was suggested, and what I also saw when I walked around, was each cell, each grid cell, uh, is a vertex. I guess many of you guys are starting there, right? So each ij will be a vertex, and then maybe I would uh, the most natural thing is put an edge between every adjacent pair of cells or something like that. That's not how that works. Right? We can kind of set up a grid graph, and of course we'll only put the vertices of the allowed cells from the racetrack. Okay, so I suspect many of you had this kind of idea. Okay, but on the other hand, no one felt like they solved it. Okay, so what was missing? Yeah.
I guess I don't know how to incorporate velocity.
Yeah, okay, so if the car could only go one step at a time and go to adjacent cells, this would model it perfectly. But what makes the question trickier or fun, or however you look at it, is that the cars can change velocity by one in each direction each step, right? So somehow I need to know that, what is my velocity when I'm on this cell? Am I already going 2 miles an hour? If so, or to the right, in that case, I'm actually allowed to go all the way here or something, right? And am I going 3? Then I can actually make 3 hops and so on and so forth, right? So there's, and of course, shortest path, all we can really do is set up graphs and then find things, right? So I guess one option is you can try to hijack the Dijkstra and BFS algorithm and try to kind of add in velocity or something, right? You can imagine trying to make a long sprawling algorithm. It's not maybe impossible, but certainly I would never ask for a question like that. So I guess the question then is, how can we be a little bit more clever about sort of embedding this extra information, right? So we always think, we often think of shortest paths as paths in a map, and we think of vertices as locations. That's the most natural metaphor. But a slightly more general metaphor is that vertices correspond to states and edges correspond to transitions and changes of states of some kind, right? So something similar once happened, for example, with American reachability. Okay, so the question is, can we try to identify the right way to describe states, which is maybe more than just a grid cell? Maybe your graph is bigger than n squared in size. That could help us account for velocities. Oh, okay, sure.
Create copies of the graph.
Oh, okay, so we can try to create copies of the graph, and then what will a copy of a graph correspond to?
So the different velocities. So I guess the vertices would be copied, but the edges would be different based on what velocity is associated with that.
Okay, so you want to take kind of our original idea and make one copy for every sort of velocity. Okay, so we'll make a graph G equal to VE, where at some level, sort of V will kind of be thought of as a tuple. So one is sort of the sets of, I'll just write at a high level, velocities times the grid cells. Okay, so okay, let me expand further. So a vertex might look like might be encoded like x, y, I, j, where x represents the x velocity, y represents the y velocity, the cell I is equal to the x coordinate where the car is right now, and j is equal to the y coordinate. Excuse me for my handwriting, but I guess you guys are used to it by now. Okay, so we sort of lifted, and we were making a much bigger graph because there could be many velocities. We'll talk about how many velocities we worry about in a moment. But what we're doing now is, what was hard was that, the first initial point of view where I'm only focusing on the vertices as cells, and it wasn't clear how to incorporate, velocities sort of into the input of a shortest path algorithm. And that sort of creates a lot of headache. But we're taking a step back and saying, oh, all the information that's available at a single point in time is really the x velocity, the y velocity, I and j. Those are really the states in the game. All right, so what would okay, so hopefully that makes sense for vertex set. What would an edge sort of look like at a high level?
The different cells that you can reach based on the x and y velocity of the graph.
Yeah, so maybe edges would have the form, I guess I'll write x1, y1, I1, j1 would be sort of where the edge is going from, and it's going to x2, y2, I2, j2. Okay, and And okay, so the rules are like, okay, the car can only change by 1 in each direction for the velocity. So I would write, such that the absolute value of x1 minus x2 should be less than or equal to 1, right? Because I can only change the x velocity by 1. The y velocity should also only change by 1. And then now maybe I should ask, how would I2 and J2, what are the rules kind of constraining I2 and J2 and stuff like that? Yeah. Yeah. Okay, that's one is I guess on the racetrack, so it's set to true in the array. Uh, but that's not the only thing that's kind of constraining our choice of edges. Yeah.
I2 equals x1 plus I1.
Yeah, I think actually the rule is you get to change the velocity and then you get to add it. So it might be plus x2, but yeah, same idea. Okay, so that is that's the high level idea. So what we're doing is, instead of just worrying about grid cells and shortest path on the grid, we're doing it in a slightly larger state space where the states are sort of following the rules of the story, rules of the game. And I guess, we just need to maybe calculate how many velocities we really need and how many edges we have in this graph in the worst case, right? So if you have, yeah, I guess at a high level, then how many vertices might this graph have? I guess as a function of n. Yeah. At the very most, n squared. Why n squared? Okay, so we have n choices for I, n choices for j. But what about x's and y's? There could be lots of different x's and y's. Yeah, Daniel? You mean x can be at most n, or maybe between n and negative n or something. Right? Maybe it's a really complicated track where you have to go backwards. I don't know. Okay, so I guess conservatively, there's at most n to the fourth coordinates. Okay. And then how many edges would there be? So there's n to the fourth vertices. So n to the 8 would be a conservative number of edges, since that's the number of vertices squared. But maybe we could do a little bit better. Yeah. Well, no, not necessarily. First of all, we already have way more vertices than white squares now because we have one vertex for every white square combined with the velocity, uh, a choice of velocity. Or maybe you can try to argue like if I fixed the starting point of the edge and I asked how many edges leave it. Yeah.
You can make the most 5 moves, so plus minus x plus minus y.
Yeah, so actually a particular sort of combination of xy coordinate and velocity uh, actually only has a very limited number of moves because it can only change each of its velocities by plus or minus 1 and or 0. And then based on that choice, it has to go to a particular cell because you add the velocity to get to the cell. So maybe that's actually 9 or something, but 3 by 3. But it's actually only a constant number of edges leaving any particular state. So if the race car is going 10 miles an hour and 11 miles an hour, it can only go to a couple of different velocities. Okay, so there's actually kind of a constant number of edges leaving any particular vertex. So you'll get the number of edges at most number of vertices, which for us was n to the fourth. Okay. Yeah. Okay. This doesn't matter too much, but some students have I've given this as a homework, given more time before. Some students have observed that in order to get up to n miles an hour in one direction, you have to first go 1, 2, 3, 4, 5, right? And so by the time you get up to n, you've already gone n squared total distance, but the grid is only n wide. So really the max, once you get to square root n, you must have gone roughly n units in the x coordinate direction, because 1 plus 2 up to square root n will give you roughly n. So actually you really only have to check your velocities up to roughly square root n, and that would decrease some of the counts, but that's slightly besides the point. Okay. All right, so much for that problem. I like it, but I don't know. Okay. Yeah. Oh, okay. 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 Yeah, maybe I didn't do a great job. The rules are that you're allowed to go through the gray squares. Uh, no, I mean, you like the as long as look at this picture. Uh, this line is definitely going over a corner. Not that you guys can see the picture well from back there. I guess otherwise, if you wanted to change the rule or go with your rules and say that you can't trim any corners and it has to be fully on the interior, then probably what we would do, actually, yeah, let me ask. Okay, so I described roughly the solution. If you're allowed to trim corners, I'm not worried about this leaping over. But if I wanted to do this harder or seemingly harder version, at least at a high level, how might I try to adjust my construction? I don't know if it'll be very fast, but I'm sure we can make it a polynomial. So maybe every time we're thinking of creating an edge in the previous tense of the word, we could do some kind of calculation to see if we could kind of walk along the straight line. We'll do some calculations, some math, and see if we're ever lying above an invalid square, and we'll figure that out. That might add an overhead of n or something if we don't have a very clever algorithm. But we could still follow this construction and then just locally check each edge to see if it's clipping a corner of a gray edge or something like that. And that'll be some painful but otherwise localized subroutine. Yeah.
So just do something that takes like maybe a long time, but you only do it once per each edge. So whenever you're getting an edge, it's some constant times n operation.
Yeah. I mean, if your subroutine took constant time, if it was a clumsy constant but took constant time, then we would just have a constant overhead. But I don't know, maybe it could take n squared time if you have a long diagonal and you have to check n squared squares along or I guess it would be closer to n squares along the diagonal. So maybe the subroutine would take n times. So every time you try to create an edge, you pay an extra n. So you lose a factor of n or something. But yeah, okay. So roughly you would look and be more careful about creating edges, but at least a high level, so you could actually solve that version of the problem too, from what I can tell. Okay. All right. So this came out when I was maybe closer to your age or something, but I don't know if you guys have seen this YouTube video called Algorithm March. It's a Japanese video where you have a bunch of people lining up. You're welcome to just watch it instead of solving this problem for the next 30 minutes. It'll probably be more interesting if you do. But roughly okay, I'll just read out loud. It's now time to line up for the algorithm march. This dance was originally developed by a Japanese comedy duo, Itsumo Koko Kara, for the children's television show Pythagoras Switch. The algorithm march is performed by a line of people. Each person in line starts a specific sequence of movements, one measure later than the person directly in front of them. So it's like a whole bunch of like really simple sequences, like they go like this, or they go like this, or whatever. But like one person would do it after another. So anyway, just watch it. Okay, thus the march is the dance equivalent of a musical round or canon, like row, row, row your boat, or I don't know. Okay, proper etiquette dictates that each marcher must know the person directly in front of them in line, lest a minor mistake lead to horrible embarrassment between strangers. Suppose you are given a complete list of which people at your party know each other. Okay, I mean, if this is confusing. Okay, the problem is to figure out the largest number of party goers that can participate in the algorithm march. For this problem, design an algorithm or show it's hard. Okay, so I think the most important thing is, so you're at a party, there's a lot of people there, and you're trying to find a set of people that you can line up in a line where each person knows the person in front of them. Okay, so I give you like the social graph of who knows each other, and you want to try to figure out if you can make a very long line so you can have a fun algorithm march. Again, it's a funnier problem if you've seen the video. Yeah.
So it's always a line, or is it straight?
Oh, you're trying to make a line of people.
Just a line.
Yeah.
So since that you are given a social graph and you mean that the person directly knows the person in front of them. So which means that for each two persons has to have an edge between the direct edge in the social graph.
Yes, yes. So well, basically, the story is you have people at a party, and I give you a long list of who knows each other,
Okay.
and then out of that, yeah, which you can think of as a graph, and out of that list, you want to find sort of a long way to line up the people so they all know each other.
So like if I go from A to B and B could go to C, it doesn't mean that A knows C.
Perfect. Yes. So A has to know B, B has to know C, C has to know D, but A and D could be strangers.
Okay, thank you.
See if I can find this.
This is super high level. What is this video?
Well, where does the tree come from?
You said we were given a social graph.
Okay, or here, scroll up a little bit. I meant what I meant to say was well, social graphs aren't trees, are they? But yeah, in general, I give you a list of all the pairs of people that know each other. That's what I meant by social graph. I mean, I just meant I give you a list of all the friendships. Everything else is otherwise a strange set of strangers.
Okay, I see.
I don't know if it's like the best like time complexity. So like if each person is a vertex and then you copy the vertices by how many people there are, and then like
okay. So you want to make like okay. So you have clones of people. I guess you're making n copies of people.
Yeah.
Okay. So and then I guess you'll want to draw edges. The edges will be based on.
Yeah. So like whoever knows this person will have an edge.
Okay. So then it'll be like this, like this, like this.
Exactly.
Okay. But I think the one tricky part you run into is that the first person, Bob, maybe you go there first and then you go to some other friends and then you go back to Bob.
But would Bob know himself? Like, would that be in the list? Oh,
Oh, I mean, each person can only be in line once.
Yeah.
So you could, because you're kind of doing longest path in a DAG. That would be great, except when you duplicate, you lose the part where people can't show up twice in the list. I guess unless you did some weird algorithm figure eight or something, which might be possible, but is beyond the scope of the question. Question? Yeah.
Like, can we just do a Hamiltonian path?
Yes.
That's it.
Mm-hmm.
So just prove it is NPR.
Mm-hmm.
Oh,
yeah.
So I done.
Yes.
So for algorithms like longest path or Hamiltonian path, are those directed graphs or can they be on undirected graphs as well?
I guess we can treat it as an undirected graph.
Okay.
So you can treat the list of friends as like undirected. Like if A is friends with B, then B is friends with A. Like a.
Okay.
Yeah.
I'm like, if it's not, then we're gonna feel real dumb.
No.
So you want to reduce it to that level. So if you just like this one, maybe simplification. But this is not necessarily general. Not necessarily a general. Because the social graph is in the same type function. Like by parts of it. There's like two rows and then or arrows.
What does it have before?
Oh, so these are two similar, same set of vertices, and then they and edge connecting A nodes B. Yeah. I mean, like, well, if you can solve it this way, why would you want to look at empty hard? Maybe it's the easier one. Yeah, because like maybe not every general map can be reduced.
How are we doing? Have people figured out? People want to keep working a little more on it? Uh, who wants to keep working on it? Okay, who wants to just discuss it? Okay, 30% to 0. So 30% wins. Uh, okay, all right, so you have two choices. The problem, you can try to come up with an algorithm, or you can show that there probably isn't going to be an algorithm. So I thought I would at least ask who tried to come up with an algorithm. Okay, one person. And then who thought that it might be too hard to get an algorithm? Okay, say maybe 50%. Okay, and there's something else going on there. Okay, all right. So it is actually hard to do. So, but how did you guys argue that maybe this problem was hard? Uh, in the back, since I've already called. Yeah. Oh, okay. So okay. So the idea was longest path. I overheard this quite a bit also when I was walking around. Um, okay. So what's the idea? You have all these people. Um, uh, and some of them know each other and some don't. Okay, so we're looking at undirected graph where each person is a vertex and each edge represents a non-strangers, so friends, I guess. Um, and you want to figure out how to line them up where every adjacent pair is friends. So that maps to, a sort of path in this graph. So, if we were going to be careful, we're going to say, okay, every path in this graph, going from end to end, that gives a line where every two, it would be kind of a boring sentence. And reverse, if you had a long algorithm march, you would get this path. It would basically be boilerplate. Um, okay, so that was a longest path problem disguised basically as a silly joke. Okay. All right. Okay. So that was also these are all from the Erickson book. Okay. Any questions about this? All right. What's next? Oh, I shouldn't choose ones with small font. Let me move this. Okay. All right. This one is just going to be an algorithm. I was too lazy to replace the text with the usual algorithm or hard. So let me read it out loud. So I guess you're given this game. Apparently it has a name, Bankin Smile. I give you an n by n grid, and every grid set has some value, plus or minus something. And I guess the rules are simple. You can you have like one token that you get to place on any grid to start. So in this example, the token is initially placed here, and then you're allowed to go down and to the right in part A. Okay. So in this solution, they go down, down, right, down, and I guess they leave the cell. And so the total score would be, if you can see it, oh, maybe I should make it bigger. 8 negative plus negative 6 plus 7 minus 3 plus 4. What does that add up to? Okay, 10. Good. Okay, so that's the rule. I give you an n by n array of values as input. And the goal is you can just pick any square to start, and you can only go down and to the right and try to get as many points as possible. Okay. And then I guess I'll just mention part B in case you finish part A quickly. Part B says now you're actually allowed to go down, left, or right. Okay, so you can't go up still, but you can go left or right. But the only rule is you can't revisit. But the additional rule is that you can't revisit the same square. So in other words, if you go down and then you go to left, I think you're left. Okay, you won't be able to go right again because that would revisit your last square. Okay, so in version 2 of the problem, you can go left or right, but you can't revisit any squares. So sort of once you commit to one direction for the rest of that row, you're stuck in that direction. Okay, but you can potentially snake around. And okay, so
not necessarily
yeah.
can you exit on the right side?
Oh, good question.
Like, do you need to exit out?
You can exit, I guess, any side you want.
Okay, but
Good.
you have to exit the grid.
Well, I guess eventually you'll be forced to because you can only go down and to the right.
Okay.
Oh, that's what you're saying. Yes, you have to. Oh, yeah, you can't just stop on a positive one, I guess. Yes, you have to exit the grid. All right. So two clarifications. In this game, you do have to eventually exit the board. You can't just like stop on a big number that's surrounded by negatives and stop there. And the other rule is, but you can exit to the right or below, or you can exit on any side. Okay, so those are questions about how the game ends. Exits when you exit the side of the board.
The game you're typing right. So like once you from the minus one we regular 7 6. This is just yes. The longest and then it's so I think you can miss the edge of these two teeth, and then you can put the start to every single one of them, and you find the longest. And each edge, suppose like this goes to -1, then this edge will have -1. And now I want to find on this bit in that deck because you can only go down. Oh yeah. So this is yeah. So longest why is the longest? Oh, like yeah, you lost points, right? You want most longest, like yeah, yeah, most.
let me just briefly check in and make sure we're roughly going in the right way. So you already know that it's an algorithmic question, so I won't bother with that one. But if I told you that it's either a change the input or an identify the subproblem, and I ask kind of which path you're pursuing, if I may ask, how many people are trying something that I might classify as identifying the subproblem? Okay. Oh wait, sir, can you do that again? I didn't. Okay, that's like 20%. Okay, and what about like change the input? Okay. That's, I would say 40%. Maybe this was 30%. I don't know why I care. Okay. Uh, I would say that okay. Some of them are kind of both right. In the sense that if this was a completely blank slate, I would have thought of it as a change the input kind of problem. However, we have done some similar problems before, so maybe you're. So I would have thought of it as identifying the subproblem kind of thing originally, but we've done some similar problems before, so maybe you're also changing the input to an algorithm we've already done, which is really based on identifying subproblems. So it's a little bit in between. We'll give maybe a couple more minutes, and then actually have.
Change the for the European. You can do it. So you hit the left edges and hit another part. From the because the only cycle that can be called is something. Maybe I'm not really proof this one. I'm going one direction. There you can go. The channel direction is that. So yeah, there was a this is the cycle. Yeah, this is. But this is the cycle. Then that. You don't know which one you want to go first. And maybe we'll remove the cycle. Change it to free. How do you change it?
Okay, maybe in the interest of time, we can start discussing solutions. Sorry if I didn't leave enough time to work on it. Okay, so part A, you can go down and to the right. Does anyone want to share their approach if they solved it? Yeah.
There's a source and a target, and then I connected the source to every cell, and then for every edge between every cell, like down and right, with
Okay, so you're imagining some kind of graph that starts with a
corner connect to the target.
okay. Okay, so okay, it's going to get a little bit messy. Okay, so the idea that was suggested was we should okay, but oh, so once you create the graph, what algorithm would you kind of use?
Since it's a DAG, we want to find the longest path in DAG.
Okay, so we're going to try to reduce it to one of these flavors of longest path to in a DAG. So first we uh, create the DAG. So what was suggested was uh, roughly we'll think of each cell as a vertex first, and I'll draw edges based on kind of where the tokens can go. So I've tried to kind of draw an edge whenever it's going to the right and whenever it's going down until I got bored on the right hand side. Okay, so that sort of sets up a DAG. Everything's flowing this way, so there's no cycles because you can't go back up. And then you can start anywhere, so we can create like a super source and add edges into every cell. I'll only draw a few because it gets kind of messy. Right? We'll draw an edge into every cell, and then I guess you can leave from one of the boundary cells only when you step out to the right. So it would only be um, these sort of boundary cells that can go to a super sink. Okay, so that sort of sets up a DAG for us. Okay, and now you kind of want to get some kind of maximum weight thing. So you can do this in different ways. One is that you can think of the weights as being on the vertices, and every time you go to a vertex, you get that weight, right? So this would be kind of similar to the maximum reward, or was that on edges? I don't remember. Have you ever done longest path with weights on vertices before? It's kind of, well, yeah, that's true. That's true. Although the algorithm's different, yeah. But project selection did have values on the vertices. So there's two different ways you can do it. You can either write your dynamic programs that interpret the weights as being on the vertices, or you can kind of maybe think of the edges being weighted by the cell that you're going to, or something like that, and then do sum of weights along a path. So it could be sum of vertex weights or sum of weights along the path. So uh, I think we only did unweighted in class, so what we would have hoped for is you would kind of have to rewrite the DP a little bit to adjust for weights. So anyway, so step one would be to set up a DP. No, set up a DAG. Okay, maybe step two would be writing uh, the usual kind of max weight path. In a DAG type of dynamic program. Okay. So I won't write it in full because we don't have too much time. But just eyeballing this, and if this was an n by n grid, okay, and I don't know if you guys remember, but doing longest path in a DAG, that was one of those times that are linear time because roughly you explore every outgoing edge once. So you usually get these algorithms that are linear time in the DAG size, but here we've kind of created a DAG based on the story. So what would that running time come out to for this problem? Yeah, n squared. Yeah, there's n squared vertices, and each cell can basically only go in two directions. So it's like two edges per cell plus n squared source edges and n to n sink edges. Okay, so it'll be n squared vertices, n squared edges or so. So you get an n squared running time. Okay. Did anyone figure out part B? So part B, you can go left or right. Yeah.
So I didn't make a graph out of it. I just did dynamic programming directly.
Okay. Yes.
And
Yes.
then I just marked as cells visited. So that was just kind of algorithms in
Oh.
these cases.
Oh. Interesting.
Like
Okay.
if going left, you've already visited that one, then don't check that.
Okay. So let me make two comments. First, for the first problem, I described it as setting up a DAG explicitly and then running a graph algorithm on it. But you could have also just created a dynamic program kind of directly on top, which is implicitly doing something similar, where you're exploring going to the left and going down. That would also be just fine. That also. Okay, so part two though, it might be a little bit trickier to set up a DAG, but uh, yeah, you can try to do a direct DV. Now, and then as a base case, you don't want to avoid what you've already visited or something like that. That was a suggestion. The only thing though is that, okay, so if you're trying to do some kind of dynamic program, then my guess is that you'll have some problem, sub-problem, right? And this will probably be the max weight starting from ij or something. That'll be your sentence. So the only thing though that I'm slightly concerned with is that if this was your sub-problem, how would you know which cell you came from? Because in a sense, if I'm implementing this kind of sentence, oh, I'm at ij right now and I want to find the best path remaining, right? But that sentence doesn't tell me much about where I came from before if that forbids me from a particular cell.
So for mine, like the grid was a global data structure. And so
Okay.
one of the fields for each cell in the grid was if it's visited or not. So every step in the recursive algorithm can check the global grid, see, oh, is the one next to me visited.
Okay, so two things to be careful about there. On one hand, you can visit the same cell from different directions and have different states in the global algorithm. So if you're only solving that subproblem at that cell once, and it's just ad hoc depending on where you came from, you won't be exhausting everything, right? Because you could have come from the left, come from. Alternatively, if you sort of put that whole state into your problem size, now you have a huge problem state. Um, that said, rather than doing a global state, we can just try to add a little bit more information, which might be maybe some kind of flag that tells me if I'm coming from the left or the right, or top or bottom or something. So yeah, some constant amount of information to keep track of where I came from. Did I come from above? Did I come from left? Did I come from right? Or did I just come from the source? Right? And if I came from the left, I can only keep going to the right. If I came from the right, I can only keep going to the left. If I came from above, I have all choices. If I came from the source, I have all choices. So, okay, I don't know what's the most slick way to do this, but just add a little bit of constant information to keep track of that previous direction so you kind of know what you're allowed to do next. I'm only sketching at a high level because we're out of time, but hopefully that makes mild sense. Okay, all right, that's all. We'll do something similar next time. And yeah, so these are all problems from Jeff's notes. They're really great, so I encourage you to try them out.